Hey everyone, in this lesson we're going to look at interference a little bit more. We're going to look at interference patterns we've kind of talked about a little bit before, and we'll go into a little bit more detail with I ended up describing a little bit of it previously, but you'll get a better exposure to it here. And so we're going to look at interference patterns in water waves, and then also, spoiler alert, with light. Destructive interference, we know that, and constructive really, but we know that waves and light both do this. So today, a little more detail about those interference patterns. So if you have a single wave source going out, you can picture the crests and troughs. If it's water waves, water moved up from where it normally sits, and water dipped down from where it normally sits, right? The crest is up and the trough is down. With sound, it can be like high pressure and low pressure, things like that, higher pressure and lower pressure. And so if you had two of these going, we talked a little bit before about how you'd have spots where there's always destructive interference, and spots are here, the destructive interference, and spots where there's always constructive interference. So where there's always destructive interference, called the nodal line, and where there's always constructive interference, so double high waves and double low waves, that's your antinodal lines. So I mentioned this previously, but hopefully this will give you a good visual of it. But basically, you look at the distance a wave travels to get to a spot, right? And if they're arriving in phase, then you're getting constructive interference. And if they're arriving out of phase, you're getting destructive interference, right? So with an interference pattern like this used to be a really awesome interactive simulation. I have to just show you the results that you could have pulled from it. Would have been basically the same as doing a hands-on physics experiment, but the computer world killed Flash programs because it was some kind of security issue or something. And so I just have the results here from it that we can look through. But the interactive simulation, you're able to put this little meter and this little sensor anywhere, and it would tell you the length from here to here and the length from there to there. Okay, so this is called, if this is source 1 and this is point P, then this is like PS1. And if this is source 2 and this is P, this would be PS2. These two lengths, okay, path lengths. And so, you could take a bunch of information, data from it, and analyze it and figure out what the link is about destructive and constructive and destructive interference. Okay, so this means the absolute value. So just the size is all that matters. Doesn't matter which one was bigger, right? So that's a math trick to just get the value of it rather than have negatives. But along here, these spots you can see would be spots where you'd have antinodal lines, and then here you'd have your nodal lines, so constructive and destructive interference. So just a little simulation that does still work here. Load it up for you here. This is going to be with water waves. First time interference and waves. And actually this one, here we go. So if I get both of the droplets dripping, we get these circles going out, and this gray spot here would be a spot where there'd be no ripples. They're canceling out. If I just have one tap dripping, turn the one off here. There we go. So just one dripping, there would just be ripples. And so if you're in a canoe, you'd be going over the wave and then down and up and down and up and down, right? With more ripples being added to the surface, you actually get spots where there's no waves, which is really odd, right? There's actually more energy of waves being pumped into the surface of the water, but these guys here are canceling out. The reason for that is an up wave would be arriving at the same time as a down wave. You can see how they're offset from each other, right? So you can see that very clearly there. So here's the number analysis of this. Excuse me. So the values, the measurements ended up being this along your nodal lines and along your antinodal lines. So then the task is to sort of analyze this out. What is that path difference? What is that path difference in terms of wavelength? That's the interesting part. Okay. So it turns out that your path difference is 5, which if you divide this by the wavelength of 10, you get that it is half wavelength. And then this one is, divided by 10, you get 1.5 wavelengths. And this one is 2.5 wavelengths. So all of the spots where you have constructive interference, destructive interference, you have a half wavelength difference, right? And in this one, we had these values for the path differences, and the fractions of wavelengths were always whole multiples, okay? So you can look at this as like odd multiples of a half, basically, and this one being like whole multiples of a wavelength itself, right? So you can see those values that are on the chart above. This isn't new. We already revealed this in the chart above. And so, yeah, that's the idea that you know now that for destructive interference, you need to be like an odd multiple of a half wavelength. In other words, you have to have a crest driving with a trough, right? I showed in a previous lesson the pattern where you have crests and troughs, and another one just like it. And then if you move one of them a half a wavelength, so a full wavelength would be from this spot to this spot. So if I go half a wavelength, we end up with destructive interference. So that relates perfectly to that previous description. So if we were to look at a spot along this nodal line, we'd be expecting this to be an odd multiple. This is a nodal line, right? So this would be an odd multiple of a half wavelength. So because it's the first nodal line, because there's only two shown, or like one on each side shown here, yeah, that would be 0.5 wavelength path difference. So literally the difference in the length of these two green arrows would be half of whatever the wavelength is. In this spot here, you can see we're at a first antinodal line, right? So this is the central antinodal line. This is the first one to the side, they call it, right? And then in the center here, it's equidistant because it's like an isosceles triangle, right? So that would be a path difference of 0, right? Their central antinodal line. So that's the kind of stuff that, just to see it in action in this simulation, that's the kind of thought you could have, kind of thoughts and analysis and so on you could have when looking at a simulation like this, right? So kind of virtual physics. So it's obviously interference patterns are happening with waves. And so the question is, does it happen with light? So with Young's double slit experiment, basically, spoiler alert, this is found to happen with light, right? But if you look at the wave particle debate back in the 17th century, it was considered a downfall of the argument of wave theory. It was that, like, okay, well, why aren't there interference patterns like waves do? And because interference patterns weren't easy to see. And I'll show you why in a couple of pages. There's a little bit about it here, actually, but Thomas Young was the first person that used a single light source with two little slits, and so that made it so that you'd have the same phase of light, like monochromatic, and they'd be the exact same light source coming through, same phase and everything, and that was a big part of the problem, of course. A big reason why you don't see it normally in life is that light is so random, right? But anyways, yeah, confirmed. Light and dark bands on a screen, constructive, destructive interference patterns with light, right? So you're like, yeah, very wave-like properties, right? So laser shining between two slits is a very easy way to do this now, but of course there weren't lasers back then. But if you think of particles of light, think of like paint-soaked tennis balls being, thrown between two or through two open doors. Right? What would you expect to see? Well, you'd expect to see two blotchy spots corresponding to the doors, right? But when you look at light, you see this kind of stuff, okay? So just, look and absorb and see this, pattern. When we look at the double slit, this lesson, we're pretty much only focused on this area most of the time. And eventually we'll see the whole picture where we have this section that's twice as wide in the middle. And then interference within it as well. Basically, this tiny interference pattern. There's a little slit there and a little slit there, little bright spot there, little dark spot, little bright spot, little dark spot. That's continuous, but there's spots where it fades out. Okay, these are the extra details we'll see later with single slits, which is very weird to analyze. But anyways, we're focused mostly on right now this idea of the dark light, dark light, dark light. And then there's an additional pattern of dark and light later on, okay? So anyways, constructive and destructive interference with light. And obviously, it's not the two blobs of light like you'd expect if it was a particle. And so clearly, this is more evidence of wave nature of light. So, and relate this back to the finger thumb interference fringes or interference pattern that we saw, right? That was so yeah, that one is obviously a single slit, which is weird to think of why that's going to happen, because you don't have light coming from source one or slit one in landing and so on. But we will make sense of it soon. Spoiler alert, I guess it's to do with the Huygens wavelets, right? If you think of a row of a bunch of wave fronts, even though it's a single slit, we can think of those Huygens wavelets as little sources. Okay, so that's the key to analyzing why it happens, and actually pretty awesome direct evidence of the idea of Huygens wavelets not just being theoretical, right? But we'll get to that later. So again, about why we don't see this in everyday life, rarely would you see two in-phase single light sources overlapping, right? There's billions of electrons doing all sorts of things, so there's all sorts of phases and whatnot of light coming at you. And light is a really high frequency, right? And so it turns out the higher the frequency, the more compressed the pattern gets. And so it's really just hard to see it, because it's, if you did ever see it in nature, somehow there was a in-phase single light sources, and two of them and so on, the chance of the pattern being noticeable is low because it'd be squished together so much. So with here, I can show you some of that stuff here. So let's go back to the simulation, and we're going to go to the slits version. And with the slits version, if this thing wakes up here, I have to pause. Oh, there we go. Slits. Come on, wake up. We're going to go to slits, and we're going to send out. This is still kind of looks like water waves here, I guess, but there's a two slit interference pattern. And then this one, pause for a second. I'm trying to think of how to get to what I want. All right, here's the light generator rather than the other one was like wave generator, I think, right? So this is basically monochromatic, in phase light coming from a nice stable source, and then it's going through two slits, and so you're getting two sources of it, right? So if you look at the screen, you're going to get like bands, right? And so depending on the width of the slits and depending on the slit separation, you're going to get different looks, different patterns that result. So even that first one I showed, you just see like single, you get light and dark, and so on, right? So depending on slit separation and whatnot, you get different patterns, right? And so see how slit separation being a little wider, right, in comparison to the wavelength of light, which is really, really small, it's going to kind of have more spaces or more bands per inch kind of thing, or per centimeter, and so it's possible for them to be crushed together to the point where you really can't even notice them, right? This little applet works kind of nice to show that. Get that guy going. And so this is just a static, image of the pattern here. And again, this is helping you see the idea of this is that big wide section we're going to talk about later. But for now, we're just focused on like bright, dark, bright, dark, bright, dark, right? And so the higher the wavelength, the more that's spreading out. Slit separation, the more it's compressing. Like you can see how this all changes, right? And if you change the slit widths themselves, the intensity clearly is changing, getting more light through, and the other patterns start to become visible as well. But just for now, we're just looking at it saying like, oh, okay, there's some details there that we're going to analyze soon, right? So this double slit interference pattern, the shaded in section, and then the less talked about in videos online, stuff like that, the single slit interference pattern. Okay, so it's a pattern within the pattern, and we'll analyze that soon. Okay. Yeah, so we can add interference patterns to the list of evidence in support of light being a wave, right? Well, there's some details later on that we'll come back to. So later we'll come back to how there's actually evidence that this can be twisted, changed. The type of versions of the experiment actually lead to undeniable evidence of particle nature of light. So spoiler alerts galore here. But yeah. So before that, though, we're going to look at some of the math of this in the next lesson. So when you look through these pages, don't worry about the math for now. Just look at the idea of the rigorousness of it, the analysis of whether or not there's going to be constructive and destructive interference and so on. And what you're going to do is you're going to see that with water waves, and then you're going to see it with light. And the point is to notice like how similar these things are, right? So these questions draw out that kind of thing about how this is obviously very, very much wave, evidence of wave nature of light. Okay. And then we'll actually analyze some of the math of it afterwards in a separate lesson. And the idea of that is just if you can calculate, you can measure the slit width, and you can measure things and predict what the spacing would be, and with water waves, and then you can do that with light as well. I mean, like it's a pretty strong piece of evidence that this is making sense and that light is exhibiting wave behavior. Okay, so yeah, that's all for now. Thank you for watching as always, and let me know if you have any questions and all that good stuff. And yeah, talk to you later.